Hello everyone, welcome to my channel Code with Aryan and to the data structures and algorithm course in Java. In the last lecture we saw how do we calculate time complexity using running time calculations of various functions. In this lecture our topic is recursive algorithms. So first question is, what is recursion? It is simply a function calling itself inside the function. For example, we previously saw something like this. There is a function fun and there is a function main. The function fun is called inside main. We have seen this kind of example many times, but in recursion the function fun calls itself within the function when this base condition is true. So in a recursive function there will be two parts, a base case and the function call. So we'll see this through an example and try to find the time complexity of these two functions and what is the difference between these two functions. We'll see. So we'll start with, let's take n equal to 3 from here, and in the first step we'll call fun1 of 3. So the first step is we call fun1 of 3. It will check is n greater than 0. In this case n is 3, so yes, 3 is greater than 0. So we will check if we'll do what the statements say. So the first statement is to print 3. Here I have written sopln as system.out.println. So the first step is it will print 3, and the next step is it will call function of n-1. n-1 will be 2 in this case. So this will be 2. So what is this 3? This 3 is an output, so we'll write output here. So output is here 3. So now what will this function call do? This function will again go here. In this case n is 2, which is greater than 0. So again it will take the first step as printing 2, since print n. So it will print 2, and the next statement is it will call function of n-1. So it will call function of n-1. n-1 in this case is 1. So what will this function of 1 do? Fun1 of 1 will do, again it will check if 1 is greater than 0. Yes, it is. So it will print n, which is 1 in this case, and it will call n-1, which is function 1 of 0. So it will print, first it printed 3, then it will print 2, and then it will print 1. So this will be our output in this case, and when function 1 becomes 0 and n becomes 0, the base condition becomes false and it will not perform any task, and it will start returning it will start returning where it begins. And this, in this case, the second one here, let us again take n equal to 3, and we'll call function 2 of 3. It will check is 3 greater than 0 or not. Yes, it is greater than 0. So first notice one thing here. First we were printing, and here first we are calling and then printing. So let us start the tracing, and this thing is called a tree. This is a tracing tree which helps us finding this output of the code. So here in this case, the second function, we'll start from fun2 of 3. It is checking n is greater than 0 or not. Yes, it is. So it will call function 2. Function 2 of n-1, which is n-1 is 2. So here it called the function. What is the second statement? Printing. But printing will not take place until this statement is finished, and this statement is not yet finished because when we called this function 2 of 2, it will again check is n greater than 0 or not. Yes, n is greater than 0, so it will again call fun2 of n-1. So it will again call fun2 of n-1, which is 1. Thus the second statement will not yet take place because this statement is not over yet. So when this function will, what this function will do is, this will check is 1 greater than 0 or not. Yes, 1 is greater than 0. So it will call function 2 of 0, and this statement is not yet finished. This statement is not yet take place because this function is not yet finished. So when we'll check is 0 greater than 0, so it will give nothing, because 0 is not greater than 0. This function will terminate. So after terminating, this means this function is done, then it will return this. So in this case, the output will be, first thing it will return is 1, because first after finishing this we will move here, so it will give 1. So our first output will be 1. Now this statement is done, like this statement is finished, then we'll go to this statement. What will this return? This will return 2. Now this function is done, so this will return 3. So in this case, it started from returning 1, then it returned 2, then it returned 3. So our output will be 1, 2 and 3. So in this case, the tree was in reverse order, like it gave the output while returning. In this case, we were getting the output while the function call, but in this case we got the output while returning. So this is a general form, and whatever this is general form in which this function is calling itself within this function. And whenever any statement is before the function call, it is called ascending time, and it is done while calling the function. And after the function, it is called descending time, and it is performed while returning. And also, if there is some operation with this function call, like if we want to multiply it by 2, this is also done while returning time only. So let us try to find the space complexity. So it is said that for space complexity, whenever this, let us take the same example. It is said that for function call, there is a stack kind of data structure used, and for each call an activation record is created, and each activation record takes 1 unit of time. So for n equal to 3, there were 1, 2, 3 and 4 calls. There were 4 calls. So for n calls, for n equal to n, like for, let's take generalization n, there will be n plus 1 calls, and hence there will be n plus 1 records created, and each record took 1 unit of time. So it will take n plus 1 unit of time, which is of the order of n, because it is because the power of n is 1, so it will be of the order n. So the space complexity is of the order n. And next, time complexity. So in here we find the time complexity using something called recurrence relation, and I'll tell you how it works. So for this function 1, we assume, let the time complexity function or the time function be t of n. Okay, then, and this is a comparison, so it will take 1 unit of time. This is printing, so it will take 1 unit of time again. And what about this function n minus 1? Will it take a constant 1 unit of time or something else? So in here we saw this function of n takes t of n unit of time. So this is same, but it is n minus 1. This is function 1 and this is also function 1. So this is n and this is n minus 1. So according to me, it will take t of n minus 1 units of time. And we got something like t of n equals to 1, let's write it first. T of n minus 1 plus 2 units of time. So this is our recurrence relation, and we'll find the rest time complexity using this. This is when n is greater than 0. Okay, and because this was the base case, when n is less than 0, our time complexity, what will it be? When n is greater than 0, still it will just once check or compare, so the comparison will take 1 unit of time. So let's write a function for the time function. It will be like this. It is 1 when n is less than 1, and it is tn minus 1 plus 2 when n is greater than 0. So for finding the time function and the time complexity, we need to write this as tn equal to tn minus 1 plus 1. So in this case we can, if we substitute n minus 1 in n, then the n minus 1 will become n minus 2. So we can also write it as Tn equals to, just substitute n minus 1 as this, so this will become n minus 2. We can, for example, I am saying this, if Tn is Tn minus 1 plus 1, then Tn minus 1 is Tn minus 2 plus 1, right? So we'll write Tn minus 1 as Tn minus 2 plus 1, then this one plus 1. So Tn equal to Tn minus 2 plus 2. This was our one. This is our second equation. Similarly, Tn will be, if this is Tn minus 2, we can write Tn minus 2 as Tn minus 3 plus 1 plus 2. This was the plus 2. So Tn equal to Tn minus 3 plus 3. This is our third equation. So these three equation we can generalize it as, for any number k greater than 1, greater than 0, we can write it as Tn equal to Tn minus k plus k. Okay, this is our generalized equation. So we'll write and the generalized equation, and then we'll assume let n equal to k. What will happen when n is equals to k? When n equals to k, this will become n minus k will become 0, and this will be k. This will be n because n equals to k. So what was our t of 0? It was 1, so it will be 1 plus n. So t of n is 1 plus n, which is again of the order of n. So this is how we will find time complexity of a recurrence relation using a recurrence relation. So next, this is again a simple program to print this number from n equal to 3. If we take n equal to 3, this will print from n equal to 3 to 1 to 1. So you can try running this code. If you understood the previous ones, this one will be simpler. And this is a rule that one recursive call, if there is one recursive call in the function, for example this is a function, and if there is only one recursive call, this, like this function name was print, and there is only one recursive call, then the order will be O of n. This is a rule. You can try tracing the function and finding the output, and also finding the time complexity using recurrence relation. So this is a recursive sum. So we are again going to write the tracing tree for this function. So at first let us take n equal to 5. Okay, and first we'll call sum of 5. Let's start here. Sum of 5. What it will check, is n equal to 0? No, n is not yet equal to 0, so it will return n plus sum of n minus 1. Sum of n minus 1 is 4. N was 5 here, so n will be 5. So now this will do. Now we call sum of 4. So what sum of 4 will do? It will again check, is n equal to 0? No, it is not equal to 0 yet. So what will it do? It will return n plus sum of n minus 1, which is sum of 3. This will be 4 this time, and this will again check, is it equal to 0? No, it is not equal to 0, so it will do return n plus n minus 1. So it will return 3 plus sum of 2. It will again check, is it equal to 0? No, it's not yet equal to 0, so it will return 2 plus sum of 1. Is it equal to 0? No, so it will return 1 plus sum of 0. So now n has become 0. So what will it return? It will return 0. So this will return 0. So what is this returning in total? This is returning 1 plus 0, which is 1, to sum of 1. So it returned 1 to sum of 1. Sum of 1 became 1. So in total this became 3. So what will be returned to sum of 2? Sum of 2 will be given 3. So this 3 and this 3 become 6. So this went to sum of 3 again. Now this 4 and this 6 became 10. So this 10 was returned to sum of 4, this 15 and this 10 became 15. So this was returned to sum of 5. So in total we got sum of 5 as 15. So this will be our final output. And in here, how many function calls were there? 1, 2, 3, 4, 5, 6. For n equal to 5 there were 6 calls. For n equal to, for generalization n, there will be n plus 1 calls. So each call will take space of one activation record, and the space complexity will be order of n. Also the time complexity will be order of n, because the time complexity also depends on the number of calls. In here we can also see that the function performs one comparison, one addition and one recursive call each time. All of these are constant time function. Only thing that grows is number of function calls. So for n calls the order will be O of n. Then the next function is factorial. How do we calculate a factorial function? So what is a factorial? First of all, factorial is, for example, factorial of n is something like n into n minus 1 into until it reaches 1. So for example, for calculating factorial of 3, we'll call factorial of 3 first. It will check is it greater than 0, it will check if it is equal to 0 or not. No, it's not yet equal to 0, so it will return n into factorial of n minus 1. So it will return n into factorial of n minus 1, which is 2, and in this case was 3. So factorial of 2 will again check is n greater than 0, and it will again check if n equal to 0. No, it's not equal to 0 yet, so it will not return 1, it will return n into factorial of n minus 1. So it will return 2 into factorial of 1. So this will again check if it's equal to 0 or not. No, it's not yet equal to 0, so it will return 1 into factorial of 1 minus 1, which is 0. So now it became 0, so it will return 1. So what this became? This 1 into 1 became 1. So this will be returned to factorial of 1. So what we got? 2 into 1. So 2 into 1 became 2. So this will be returned to factorial of 2. So it will factorial of 2 now got the value of 2. Now this became 3 into 2, which is 6. Now the 6 will be returned to factorial of 3, and now factorial of 3 has the value 6, and this will be our final output. So next is Fibonacci series. So let us understand what is Fibonacci series. In Fibonacci series, the first term is 0 and the second term is 1. The third term is determined by the summation of previous two terms, which is 0 and 1, which will be 1. The next term will be determined by the summation of previous two terms, which is 1 and 1, which will be 2. The next term will be 1 plus 2, which is 3. Next will be 2 plus 3, which is 5. And similarly it will go 8, then 13, and then it will move on. So for example, we'll again trace this function using the recursion tree, and in this case notice we have two recursive calls each time. So let us dry run the code and draw the tree for this. So this is kind of a table for Fibonacci series, which as n grows from 0 to 7, the Fibonacci of n becomes 0, 1, 2 till 13, and it will move so on. So we will try dry running this code and draw a tracing tree to find the time complexity and the output. So let us take n equal to 5. First it will call fib of 5. The fib of 5 will check is n is less than or equal to 1. N in this case is 5, so n is not less than or equal to 1. It will run this statement, return fib of n minus 1 plus fib of n minus 2. So fib of n minus 1 will be fib of 4, and fib of n minus 2 will be fib of 3. this will be a plus in between, so we will add them after the tree is complete. So fib of 4 will call fib of 3 and fib of 2, fib of 3, and it will call also fib of 2. Also fib of 3 will call fib of 2, and let me write f as there is less space, fib of 1. Now fib of 3 will call fib of 2 and fib of 1, and fib of 2 will call fib of 1 and fib of 0. Also fib of 2 will call fib of 1 and fib of 0. Fib of 2 will call fib of 1 and fib of 0. And since in the last level we have all fib of 1 and fib of 0s left, and the n is less than or equal to 0, less than or equal to 1 in this last level of each call, so we will return n, whatever n it is. So in this case we have n equal to 1, in this case we have n equal to 0, in this case we have n equal to 1, in this case we have n equal to 0. This will return 1, this will return 0. So what will fib of 2 get? Fib of 2 will get the sum of 1 and sum of this 2. So it will get 1 plus 0, which is 1, and this will have fib of 1. F of 1 will return 1. So this fib of 1 will get this plus this, which is again 1, and this will get this fib of 2 will also get 1, this plus this, which is again 1, and this fib of 1 is 1 because it returned 1 as mentioned here. So this again fib of 3, what will fib of 3 will get? This will get some fib of 2 plus fib of 1. So fib of 2 is 1 and fib of 1 is 1, so it will get 2. So in here also fib of 3 will get 1 plus 1, which is 2. Here fib of 4 will get 2 plus 1, which is 3. Okay, is it? Yes. Fib of 4 will get fib of 3 plus fib of 2. Fib of 3 was 2 and fib of 2 was 1. So 2 plus 1, 3. Now fib of 5 will get fib of 4 plus fib of 3. So 3 plus 2, it will get 5. So our output will be 5. For n equal to 5, here we can see for n equal to 5, the answer should be fib of 5, which is 5. So our answer is correct. For this case, calculating the time complexity is a little difficult, so I have to make a separate recursion and recurrence relation kind of video fully for recursive algorithms, in which we can learn how to calculate the time complexity. But in this case we can have an intuitive approach for calculating the time complexity. So we can see in each level the number of recursive calls is getting doubled. For example, let us write a tree for such kind of example. Let us write a tree of fib of n. So fib of n will call fib of n minus 1 and fib of n minus 2. This will call fib of n minus 2 and fib of n minus 3. This will call fib of n minus 1, n minus 3 and fib of n minus 4. Similarly, it will call 2 more functions, this will call 2 more functions, this will call 2 more functions, and this will call 2 more functions. And similarly, it will double in each level until a base condition is reached. So here it called once. In this level there were 2 calls, in this level there were 4 calls, in this level there were 1, 2, 3, 4, 5, 6, 7, 8 calls. So 8 calls. We can find a relation between it, since this is 2, this is 2 power 1, this is 4, this is 2 power 2, and this is 2 power 3. So for example, this, if there are n calls, the max it can reach is nth level. So at the end there will be 2 power n calls. If the max reached is n, if the max level is reached is n, then the total number of calls in the last level will be 2 power n, plus some constant for other comparison and all of other constant operations like comparison and all. So here the time complexity will be order of 2 power n. So the time complexity in a Fibonacci series is of the order 2 power n. And we will learn other approaches in a video which is for only recursive algorithms and recurrence relations. So for this class, let us do till here, and in the next class we will do comparison of time and space complexities of functions and asymptotic notation. Thank you for watching the video. If you like, please leave a like, share and comment. Happy coding. Thank you.